Hi there, and thanks for joining us for Mastering the Next Generation of Vermont Science Standards. My name's Francis Vigent. I'm CEO here at KnowAtom, and I'm also a former teacher, high school math teacher, as well as an elementary and middle school science and technology, engineering and math specialist. I've been part of KnowAtom for about 10 years now, and KnowAtom is located not too far from everyone in Vermont, just north of Boston in Salem, Massachusetts, about 20 miles north. And our clients stretch all over the United States and actually internationally as well. We are really looking forward to this time to think about kind of the connection between science and the K-12 classroom, first and foremost, but the transition under these next generation science standards as we think about the NECAP assessments, preparing children for college and career readiness, and whether you're an elementary teacher thinking of students getting to that next level in middle school or middle school to high school or so on, really thinking about this from really a purpose perspective. So that's where I'd like to start. At KnowAtom, one of the things that as a bunch of educators we try to focus on first and foremost is the fact that science and engineering occurs in the elementary, middle school, and so on classrooms because it's the best environment to teach higher order thinking skills, specifically the skills to create, evaluate, and analyze the way a scientist or engineer would. And so the way we approach that here at KnowAtom is by putting children into the role of scientist and engineer and equipping classrooms to do that in alignment with the next generation science standards. So that's where we focus a lot of our time on curriculum, materials, and professional development to make sure that the classroom educator is, and also recognizing that it's not just teachers, but in fact principals and entire educational systems that have to be in alignment, but that all of these components are well supported so that when you think about what's happening in that classroom, it's really a next generation inquiry environment, and that's a lot of what we'll talk about here today. So the basic agenda over the next hour is to think a little bit about what makes a new next generation science standards tougher, some of the foundations that are different than what the previous Vermont standards entailed, how those standards link to Common Core ELA and math, and how these standards in this new kind of inquiry environment affect or may change the methods for science instruction K-12 depending on the kind of model you've previously been accustomed to. And then, finally, how the integration of these standards with practices and this focus on higher order thinking reach into other content areas, even beyond ELA and math, into the arts and so on. So without further ado, the piece to think about here is that the next generation science standards are based on the nature of science and engineering itself. And you've seen this, so when you think about the NECAPs, those inquiry portions of the NECAP assessment kind of informally show this. But with the involvement of engineering, it's going to become much more of a cycle, much more obvious as those NECAP assessments are aligned to include the next generation content as well as engineering. So the nature of science and engineering really is the foundation of the new standards. We have specific definitions for what science and engineering is now. Science is knowledge from experimentation. Scientists ask those questions. They ask questions and they answer questions by developing hypotheses, planning experiments, carrying out those experiments to gather data and form evidence-based conclusions. That's how scientific knowledge is developed. Engineers use their scientific knowledge when they identify and solve problems by prototyping technology, testing that technology to gather data about it and form a conclusion as to whether or not that technology needs to be refined or replicated. So this forms a kind of STEM cycle because the technology is enabling scientists to answer questions that they previously couldn't answer for lack of instruments to gather the data. Think about space probes, for instance. And through the development of new scientific knowledge and new technology for gathering data, oftentimes new questions and new hypotheses emerge. The development of scientific knowledge helps engineers solve problems that couldn't be solved before. So you can think about, the idea of modern medicine being built on an understanding of, basically at a microscopic level, life at a microscopic level, and chemistry and such. So medicines are engineered technology that treats disease, basically. Math is at the center of all of this because it's a tool for quantifying and communicating observations and making or pursuing problems or questions in such a way that they're logical and are able to be repeated and verified. So think about quantifying, analyzing, evaluating, communicating, all require math. And that's true in any of these pieces. So when you think about the full implementation of the standards or the curriculum alignment and resource development that went on in 2015, 2016, the 2016 and 2017 year being about full implementation, one of the issues that Vermont educators are going to be facing, and this is sometimes a bigger issue, the larger the school district, the bigger of an issue traditional models of instruction can be. Typically, it's a bigger issue at the middle school and high school level. And there's a lot of different reasons for that I won't go into right now, but a traditional model of science instruction is one where content flows through the teacher. The teacher is sort of the primary regulator and one provoking forward progress in a class, where they're modeling facts, demonstrating phenomena, explaining what, they're really setting the pace, and the student's role in that environment is to absorb everything that's being modeled or demonstrated or explained and to be able to mirror that back. And this is, when you think about the kneecap, this is what you see on the multiple choice section, right? If you modeled the fact, if you demonstrate the phenomenon, if you explain what it is, and a student is able to absorb that and remember it, then on the multiple choice portion of that kneecap, they should be able to recall the fact, repeat the demonstration, or summarize the phenomenon in such a way that they can demonstrate proficiency. Traditional models of instruction tend to struggle on the inquiry portion. And the reason is that when you consider a scenario or a unique context like you see on the inquiry portions of the kneecap, that's not something that you can just recall. It requires higher order thinking skills. It requires science and engineering practices to be applied to that scenario, because a student needs to be able to develop and use the content. You see here, a student is not developing and using the content. The students are merely absorbing and giving back what was absorbed. So when those questions like what is a metamorphic rock? That's just explaining what I was told. Where? That's just recalling the phenomenon that was demonstrated. So this is kind of an old model, it's a traditional model, but it's something that is still being taught actually in a lot of education schools. But that's changing. What it's changing to is more of a next generation model. In next generation inquiry environment, it mirrors in many ways the scenarios that you see with fictional students in the kneecap assessments. And not students following something that's given to them, but instead students authentically engaging. And here's how a next generation inquiry model works. You notice the teacher is not between the student and the content. The student is actually developing skills which they then use to develop and use the content in order to solve a problem or answer a question as a scientist or engineer would. The role of the teacher is to act as a coach to help guide from afar. Really, it's hands-off guidance. It's not. It's the kind of guidance that comes by tuning that inquiry environment. So, to guide sounds almost like there's an element of, hand-holding, and that's the thing. Is really a full release of responsibility here. There's no hand-holding. But what the teacher is doing is gradually adjusting supports. They are helping the students understand how to engage appropriately, and they're redirecting and monitoring, differentiating instruction as student teams are checking in at key checkpoints in the scientific process or the engineering design process. So the teacher's not getting between that relationship of content and students and skills and the phenomenon and so on. They're strengthening it. The expectation of the student to be able to demonstrate proficiency is to actually develop and use that content with the skills they've developed in the context of solving problems and answering questions. And so they should be able to, by developing and using the content, which is those disciplinary core ideas, be making connections and be able to relate the content with its phenomena, the sort of systems context, which is the cross-cutting concepts dimension, these new standards. Now, one of the key kind of factors is, can a student use that system behavior to describe how different pieces of content interact? So you could think about an ecosystem. Can a student connect food chains, food webs, the idea that there are different organisms in this ecosystem by looking at them sort of individually as organisms as well as producers, consumers, primary, secondary, so on, and be able to relate all of those pieces in many different ways, not only food chains and food webs, but life cycles, movement of matter, flows of energy, matter being recycled into the environment, and so on, just from a basic scenario like that. So this is very different than a student observing, and even in the case of hands-on, a lot of people say, well, we do hands-on inquiry, and so students discover and they take things apart and so on. Well, that's still a passive process, and what you're looking for is an active process, something that has purpose, that's emanating from a problem or question, and leveraging the practices of science and engineering to engage students in solving that problem or answering that question as a scientist or engineer would, using process. So the students are developing actual logical tools that they can use to pursue the problem or answer the question. So that's where prototyping and experimenting comes in, and the actual planning. Planning needs to occur first, and that plan needs to be developed by the student or student teams, maybe teams of two. So the next generation science standards are designed this way with that in mind. You have a performance expectation here, that's the standard, and then you have the skills which are absolutely necessary in order to perform that expectation, and you use those skills to develop the content, which is the disciplinary core ideas that are here, and observe the cross-cutting concepts and actually be able to connect those within that content. So that's why these foundation boxes are so necessary, these three dimensions, because they form the sort of walls of the inquiry experience. And I don't like the idea of a wall sort of hard in a sense that, it seems like there's no other components, which there are, but without them you have no sense really of where and how this performance expectation has boundaries and merit. Now the thing is that when you look at the peak alignment criteria that were developed by Achieve for the next generation science standards, you'll see that in fact the standards are intended to be taught in connection with each other. And so you're not taking a standard that is a grade 5 standard and saying, okay, this is taught in grade 5 and the grade 4 standards are taught in grade 4. You can think of them as being mastered in grade 5 or mastered in grade 4, but they have to be grouped together, not only one standard at a time within a grade level, but actually grouped with standards from grade levels prior as well as upcoming grade levels. Think of it as introducing, mastering, and reinforcing. So you are mastering standards within your grade level, but you're also reinforcing standards from prior grade levels, and you are introducing standards from future grade levels. And this is important because the NECAPs, as they are becoming aligned to the next generation science standards, are going to continue to assess grade levels prior. And if the NECAP is even replaced at some point with a next generation aligned assessment like one going on in DC or Illinois, it's important to recognize that the expectation of the student is to perform an expectation in a context that's unfamiliar, and it's going to involve multiple performance expectations, not just one. And many practices and disciplinary core ideas and cross-cutting concepts, not just one at a time. So keep that in mind. This is not something that sort of lends itself to taking old curriculum and trying to put practices into it unless the curriculum is designed for an inquiry model of instruction under the previous standards. So that's one of the key points here to success, is making sure that students, when you see these 8 practices, are the ones who are pulling these practices together simultaneously within a scientific process or engineering design process to be able to ask the question, define the problem, but then pursue it to an evidence-based conclusion by not only using a model but developing one, not only carrying out an investigation but planning one, not only interpreting data but analyzing it. The key difference between interpreting and analyzing, when data is handed to you, you can interpret it looking at it. When a data table comes to you, in order to analyze it, it requires you apply mathematical operations to uncover something within the data. For instance, the average difference in height between 2 plants, perhaps one treated with plant food and one that was not treated with plant food, and all other conditions being equal. You might have a bunch of data there. You need to analyze it to find the difference in plant height and then actually interpret that data. Okay, the analysis isn't done for you as a student. Using computation, mathematical thinking, constructing explanations, and designing solutions, these are from data. So this is your claim evidence reasoning. And that's where arguing from evidence comes in, because in writing, you're arguing from evidence, but then also there's opportunities to take your claim evidence reasoning statement, your conclusion as a scientist or engineer, and then compare that to others who are trying to solve the same problem in your classroom or answer the same question in your classroom under the same constraints, but took a different approach with different outcomes. And that's where obtaining, evaluating, and communicating information is so vital. This process of planning investigations incorporates ELA and math, as well as this next generation science inquiry environment in general, involves ELA and math Common Core standards, and all disciplines, we could throw history in here as well, benefit from the creative, evaluative, and analytical thinking skills that are developed as part of this next generation inquiry environment. So when you think about students in the classroom, for instance, these students, they've gone through some nonfiction reading to lay background for a Socratic dialogue, which was led by that teacher, forming triads from students' contributions, and not the teacher's not playing the role of someone validating or somebody who is saying right, wrong, or good, bad, or anything like this. But what they're doing is they are asking questions which require students to consider what they've read, the context, place-based connections, all of these pieces, so that that's the context that they are creating, evaluating, or analyzing in their response back to the class, sort of offering their ideas, and then the teacher's asking follow-up questions to that involving other students. Do you agree? How? Why? What evidence do you have? What connection? Where do we see this? So on. So it's not the teacher validating, saying correct, but instead they're pulling other students' contributions in to really suss out whether this is a supported claim, whether it's speculation or based on fact, and so on. And that Socratic dialogue is where students make, as a class, those, or really also solidify those concept to concept, concept to self, and concept to world connections. And so pulling that forward, you're able to come to a problem or question which student teams like these break down into lab partners and actually use the scientific process or the engineering design process to try and solve using the scientific and engineering practices that they've developed. So process and practice are different but related, and both are necessary. So sometimes the scientific process is referred to as the scientific method. Now, process is not linear. Some people make the mistake of thinking the process is linear. Also, by using process, you're not making the claim or even implying that, or teaching process, you're not even implying that science or engineering is linear. Process is just logic. Practices are tools to be able to pursue a problem or question logically. In the context of writing, we have something similar. So when we teach children to write, we teach them the tools, which are the practices of writing, word choice, voice, tone, sentence structure, and things like this. We also then teach them how to apply those tools logically to go from an idea to a high-quality published work. And so we teach them the writing process, or a writing process. And the writing process is brainstorming, pre-writing, drafting, editing, revising, and then publishing, just as a kind of a general. So you can see you need the tools, but you also need the process in order to come up with a high-quality published work. One of the kind of ways folks who really haven't thought deeply about this sometimes like to come back at process. They have to say, well, discoveries are made by accident, and you don't always have to do research before you form a hypothesis, and so on. Well, that's true, but professional scientists don't just show up at work and act illogically. They try to inform themselves. So research has its merit. They try to form hypotheses which are testable, and then they really spend a lot of time structuring experiments, planning experiments first, which they then carry out to gather data to reflect on their hypotheses. That's how they learn. And by structuring a plan, what they do is replicable. It's something they can communicate. So again, we are trying to equip children for life and an understanding of the development of scientific knowledge and the development of technology, not sort of, plan A is random, which is what the claim that, or sort of this other school of thought where process isn't necessary because things happen by accident. That's really what that communicates in a lot of ways. So these children here in this picture, they're in the role of engineer right now. They've gone through all that Socratic dialogue, and there's a problem their question is dealing with. They're taking that problem and they are breaking it down. They don't know, and this is key, they don't know the answer to the problem. They have some resources available. They have to decide how to use those resources in order to solve the problem. And so they're going to have a meeting of the minds, pick an approach, and then diagram it, build it, test it as engineers. Because if you're creating something and you can't test it, you're just crafting. You need a structured test so that you get data to reflect on that prototype, whether or not it solves the problem. Okay, otherwise it's not engineering, it's fantasy. So in this way, Bloom's taxonomy in a next generation inquiry environment has, kind of is addressed this way, where Bloom's taxonomy is traditionally remembering, understanding, applying, analyzing, evaluating, creating in that sort of 6-level pyramid where creating is the highest order of thinking. In a next generation inquiry environment, creating, evaluating, and analyzing those higher order thinking skills happen simultaneously. And that's what you were seeing here. The students are creating a plan, a nonfiction process written plan for how they are going to solve this problem. They're going to carry out that plan. They're going to, and as part of this, they're evaluating and analyzing the problem. But once they begin carrying out that plan, not only is it the prototype they've created and the process writing they've created that they're evaluating and analyzing, but it's the data as well. And then they have to form an evidence-based conclusion, a claim with evidence and reasoning, and that evidence and reasoning and claim requires creating, evaluating, and analyzing in the conclusion. So it's really important to recognize that isolating, and if you're to ask people what's the highest thing you hope for out of your science class, a lot of people will say that students can apply what they've learned. Well, in the highest, in terms of Bloom's taxonomy, that's not higher order thinking. Of course, remembering, understanding, and applying is necessary, but if you can't analyze, evaluate, and create, you really don't make it over the line. And that's really obvious, and even the historical NECAP data, when you can look at a district and you can see how well that's happening by looking at the district or even the school's performance on the inquiry portion, right? Because if you can remember and understand and apply, you can get the multiple choice, no problem. If you can't evaluate, analyze, and create, you're going to struggle in that inquiry portion because that's all it's relying on. I wanted to show you an example of a DC assessment. DC's assessments are next generation aligned. Just like the NECAP assessments, they are testing prior grade levels as well as the grade level that is being tested. Now, they're testing at grade 5 and 8, not grade 4. In other states where they have turned to DC for a model, since DC's already tested a lot of these questions and such, they have even moved their testing from 4th grade to 5th grade in that case. But so things to keep in mind that could potentially happen in the future, just as assessments are changing to match the new standards. But nonetheless, they're always assessing more than one grade level performance expectations, as well as grouping them. So you're dealing with more than one performance expectation in any given assessment. So this looks really familiar in terms of the kind of scenario that you would see in a NECAP assessment. The thing I want to point out is not really as much about the constructed response with scenarios, since you do have so much experience with the NECAP assessments, but how that plays out when it comes to multiple choice assessments as well. So the multiple choice assessments now involve oftentimes multiple choice as well as open response. Okay, so it's in a lot of ways merging what you see in the inquiry portion with what you would see in the typical selected response or multiple choice portion of the or the non-inquiry portion of the student's NECAP assessment. You get scenarios, and then you have questions, which might be multiple choice. What you see on the left is called a technology enhanced item, because the DC assessments are computer-based. But nonetheless, the point here is that it's drag and drop. You have to be able to look at organisms, think about the context, and then drag and drop them into their proper place within a food web. And as a result, explain, so this is an open response, constructed response item, where explain how energy is taking the shortest path, or where energy is taking the shortest path from the plants to the fox. In the next question that you see here, students have to use the model that's given of a food chain, and the multiple choice is not which of the following is the correct answer, which of the following describes. It's in fact there are 3 correct answers, and students need to be able to choose the 3 correct answers out of the 6. So that's a key piece here. And then once they've done that, they're asked to construct a response, an open response, using that same food chain model that's at the top to describe how matter, or there's like a relationship between these organisms and the exchange of matter back into the environment. So you can think about this in the sense of a food, another food chain. So in fact, there's a food web here that involves that bacteria that is recycling matter back into the environment. And you also have life cycles kind of coming into play here as well. There's a lot of different angles that could be taken with this. So a student needs to be able to think more deeply about the model that's given and be able to construct their own model off of it as well, and be able to explain that. So you can see the multiple choice in open responses has a very different flavor here than it does in a NECAP assessment. I'm going to show you another multiple choice. This one here continues to use those same fictional students that have been kind of cascading through the test items. You have a scenario. It's talking about how matter is making its way back into the environment and different ways that we treat waste from everyday life. And a student, again, is asked to select 3 out of the 5 answers, the 3 correct answers out of the 5 possible answers. So that's kind of the situation here. So it's not going to be as easy as just identifying, which is what those multiple choice responses under the NECAPs have historically been. And you see another multiple choice there. Sorry, not a multiple choice, but another open response based on this scenario. So that's, as this assessments become better aligned or just entirely transitioned out so that there's a next generation assessment in place of the NECAP, you should expect that that's the dominating model versus kind of the lots of quick, just identify which and what type questions that we've seen, for years past. There's a new definition of effective STEM instruction, which is important to know as a result, if you hope to master these new standards. And that is that effective science instruction capitalizes on students' early interests and experiences. So it's starting in pre-K, really. It's identifying and building on what they know. So it's scaffolding September through June intentionally, very thoughtfully, in the way that concepts are kind of being rolled out through the school year, and then also from one grade level to the next. So that's kind of how these first 2 points fit together. And it provides effective science instruction should be providing students with the experiences to engage the student in the practices, and that wording is very intentional, that it's the student who's engaged in the practices, not the teacher, and they're engaged authentically, which is what the next piece is talking about, sustaining students' interest. So they're engaged authentically, and that you have to also, I think, be honest with yourself in terms of students' engagement comes from oftentimes engaging their own ideas, not the ideas of the teacher. So again, this is that transition to a next generation model. So that traditional model is what you see in the picture on the left. Somebody pre-teaching, showing, modeling, and the students intently trying to remember, the order of what they've seen and, why they were told, to do this and what they're doing and such. So in that example, the student is not engaging in the practices. They're just engaging in remembering so they can recall. What you see on the right is students engaging in the practices because they haven't seen the solution. They need those tools to proceed logically from the problem toward an evidence-based solution. Okay, and that's authentic because nobody's shown them. They haven't seen this before. It's new to them entirely. And it's sustaining their interest because it's their own ideas coming to life. So this is what should be happening on an everyday basis in your class, not as a culminating activity, not as a quarterly kind of project or something like that. It's, on an everyday basis, and there's a kind of, way of also thinking about this is in, what I described earlier with the ELA and Math Common Core connections. That's one of the key pivots, really innovations required to meet the goals of NGSS. We have a whole webinar that talks about that in detail and goes through each of them, and these come directly from Achieve's Peak Alignment Criteria, PEEC. And that webinar you can find on our website is called How to Assess Your Curriculum for Alignment with NGSS. Now, when I'm saying this students engage in the practice should be happening on an everyday basis, you don't have to shut down your school and just do science one day a week. The reality is that lessons under the Next Generation Science Standards take place over the course of multiple days. And so you could picture your average middle school week consisting of, kind of like this, a day of nonfiction reading, a day of Socratic dialogue, a day of students planning their investigations, a day of carrying out those plans, gathering the data, and then a day of using the data to form conclusions, share out, and debrief. Now you can have it, as you become skilled at this, you'll see that nonfiction reading doesn't take an entire class period. You can actually leap into some Socratic dialogue, pick up the next day with Socratic dialogue, transition into students planning investigations the following day, have students wind up those plans and transition into carrying out the investigations and so on. That's the way it really should be occurring, but for kind of getting started with this, you can picture it this way. So this is what your week kind of looks like, and what's changing is which context the student is, engaged in. So the content, whether they are engaged as scientists or as engineers, are they dealing with a question, are they dealing with a problem? And here's examples of the scientific process and engineering design process which the students would be using to pursue the question logically or the problem logically to come to an evidence-based conclusion using the practices, those skills they've developed within the context of the content of that lesson and that unit. Okay. Now, science and engineering is iterative, and what that means is when you come to a conclusion, it causes you to pivot, whether it's in a scientific context or an engineering design context. It's very rare that a question is answered within one sort of go through where you gather data and you come to a conclusion and you can say, oh, question answered. But in fact, you come up with new information that you then have to either test your hypothesis differently, carry out more trials to verify, or really form an entirely new question or hypothesis to get at what you really hope to get at. And something similar with the engineering design process. It's very rare to solve a problem well with your first prototype. And the data that you get back from that often requires refinement. And that's important because, again, thinking about these new standards, that what they're doing is they're moving our science classrooms into alignment with the way that scientific knowledge is developed and the way that engineered solutions are engineered to problems. The way that that can look in a classroom, I'll just give you a grade 7 example. Students within one lesson, 1 week, can be learning about water cycle and landforms, water tables, the interaction between land and water, and erosion, sedimentation, so on. So there's a connection between all kinds of rock cycles, water cycles, ecosystems, and so on. And as scientists, after reading and Socratic dialogue, there's a question of which earth materials are most permeable to groundwater when we think about aquifers and the connection between what water above ground and below ground. And so breaking into teams where students are going to wrestle with that question, actually use the scientific process to develop their own plan. So what you see here is, student develop a plan, which they carry out and develop, gather data and form an evidence-based conclusion about it. In the very next lesson, they can connect that knowledge to what's the forms of pollution that we know about and how pollution at a surface level can become part of the water table, polluting the water table, so from above ground to below ground to water table, and then actually move from, a place far away to a well nearby, and thereby sort of connecting a problem with scientific knowledge, and then students can act in the role of engineer to try to address the needs of humans and trying to solve this problem by addressing the needs of a fictional town to have a low-cost water filtration device that's less than $5 and uses only 3 different types of material to remove non-point source pollution and sediments from stormwater runoff. And so you can see here the students would develop that plan using the engineering design process, which is different. There's similarities, but it's very different than the scientific process. So pulling their scientific knowledge together, their knowledge of a problem, to solve a problem as engineers, pick a particular approach. So think of different approaches, pick one of them, diagram, build and test, gather the data, and form an evidence-based conclusion as to whether this approach should be refined or replicated. Does it solve the problem adequately? So you can see it just within the course of, let's say, 3 weeks or 2 weeks, you can go from science to engineering, pull it all together. That's at least the way we approach it. That's the way that the peak alignment criteria recommend approaching it. And if you want to see any of these examples up close, you can go on our website, KnowAtom.com, and download a sample of a month's worth of sort of the teacher's lesson as well as the students' reading material, and see the materials we provide, what that looks like and such. We do have, so we have that for each of the grade levels. We have all the other units to fill out a school year, but they're just not freely available to the public because we pay our bills that way. So when you think about other aspects too of the lesson, it's not just students engaging in the practices and sustaining their interest and nurturing it from one month to the next as well as one grade to the next, but it's also involves assessment. So those plans are kind of formative and summative assessment, these plans that students are developing, right? So again, you can't give it to the student, they have to develop it. Otherwise, you'd be assessing yourself and not the student. You'd also be removing the opportunity for them to learn and those practices and sharpen them in the classroom. But in addition to that as an assessment, the plan itself, you also can use that sort of kneecap model through scenarios where you tease out different dimensions and require the student to perform the expectation in a related but unfamiliar scenario that's not the result of direct instruction. That's the key here. Okay. When you look at the ELA, just here's a quick snapshot from middle school level. When you look at the ELA technical subject standards, you can see that within that next generation inquiry environment, if the students are really being put on the forefront, as I've been describing to you, you are meeting the needs of those science and technical subject standards. Okay, things like following precisely a multi-step procedure. Once a student has designed their procedure, so that's the science side, following it when carrying out an experiment is the ELA science and technical subject standard side of things. There's also communication and writing standards, which I don't have up here, which are being applied in that environment as well. Distinguishing from facts from speculation, okay? Reasoning from judgment based on research findings, ELA, but yet happening within science time and learning. When you think of Math Common Core, there are the Math Common Core practices. So all of these, making sense of problems, persevering in solving them, reasoning abstractly, constructing viable arguments, attending to precision, and so on, all of these are required of a student to be able to engage in that environment, developing their plan, then carrying out their plan, then using the evidence they've gathered to support their, to form a claim and reason it with evidence. So again, back to that Venn diagram. The connection here with the arts is really through higher order thinking. Artists engineer communication. They make statements through different mediums, so think of nonverbal, in many ways, unless maybe poetry. I mean, it's hard to paint with a broad brush here because art is so nuanced, but art is engineered communication, and artists intend to communicate something through what they are creating, whether it be a sculpture, oil on canvas, and such. And unfortunately, many times when people think about the connection between science and engineering and the arts, they think that artists make what scientists and engineers create pretty. And that's kind of a simple, overly, it's a very basic idea, narrow definition of what art is. When you think about artists historically living in places that do not have freedom of speech, where they're oppressed and often living in exile and such, they do so not because they make things pretty, and people don't like pretty things. They end up in these situations of oppression and exile and worse because they make statements which are unpopular to certain people or with certain factions. And so a good example of that is somebody like Pablo Picasso and one of his most famous works, Guernica, where he was commissioned to create a piece for the International Art Exposition, and he took that piece and that opportunity, and he created a piece and a statement which highlighted the atrocities being committed by the fascists in Spain in this village of Guernica. And you can see it's not pretty. It's not supposed to be. It's bringing to life chaos and loss and destruction and atrocities against humans and animals and all of these sort of things. So he did this intentionally. Yes, it has sort of a Picasso aesthetic. You could attribute this to him just based on the way it's drawn, but when you look at why he created it, it was to make a statement. When you look at its purpose, again, it's not to be pretty. It's to make a statement to a specific group. It's targeted, and as evidence of this, it's often said that after this exposition, the fascists came to Pablo Picasso and they said, "What did you do here?" And he said, "I didn't do it, but you did." So you can see in that quick exchange between the fascists and the artist that this was intentional. This wasn't sort of an accidental thing that he just made this scene and sent it off, and it had this big impact almost accidentally. It was something that was very intentional, and that is the purpose of art and artists, is to make statements. And so they are engaging those science and engineering practices, the precision, the creative, evaluative, and analytical communication and thinking skills that we are developing in our science and engineering classes to make these statements and target them. And by the way, when you look at that next generation inquiry environment, it's a full release of responsibility, but there's still expectations and accountability checkpoints and redirecting and monitoring, all these sort of things that are happening. So it's really a culture of critique, and that's how artists are made. They're made by a culture of critique, whether it's formal or informal, as they attempt to make statements and target them to those who they wish to communicate with, really publicly. And so when you look at an artist, a school where artists are trained, that's what it looks like. It's a culture of critique. It's of course, you have to know how to hold a paintbrush, but a lot of people can hold a paintbrush. What they're really focusing on is choices of color and motion and medium and shape and such in order to take an idea and communicate it to a specific audience. So that's what's happening, as the artists, the faculty, are leaning over the shoulders of these students and asking questions about why they've made these choices that they've made, and what is the thinking behind that, and who are they intending to communicate to with this, and so on. So that's what high art is really about, real art is about. When you think about the resources under Next Generation Science Standards, and when you think about kind of the different components, curriculum, professional development, materials, and then that STEM learning environment, all of those resources are intended to support the STEM learning environment. When they come from the same place, they fit hand in glove. At least they should fit hand in glove. You get that benefit when the resources are designed to fit hand in glove in terms of a scope and sequence and grade level specific ordering and such. The downside of the way a lot of resources exist right now is they aren't created that way. So, you're welcome to take a look at KnowAtom resources. That's how we design resources, to be grade specific and, intentionally nurturing scaffolding really one grade to the next and one lesson and unit to the next, September through June. But when resources are kind of a kit about life science that you can use for 3 months in any grade between grade 3 to 5, that's too rough. It's too rough. There's not, there's those models are difficult to do what we've described in order to engage students in the practices, scaffold it, and have a rigorous scope and sequence to be able to introduce, master, and reinforce the way we've been describing. And part of the reason for that is really based here, that there are awareness-ready resources which are free resources. You can get them from companies in your community. You can get them from museums. People, raise money so that, students can understand the basics of what an engineer is, what they do. Doesn't mean that they know all about what engineers have solved. Same thing with scientists, what they've discovered. Doesn't mean that they have developed the skills to be able to develop and use the content to solve any problem or answer any question. Knowledge readiness is like textbooks. It's better than an awareness-ready resource, but it's just kind of looking back at all of what scientists have discovered and engineers have designed to solve problems. Performance readiness are the kind of, plastic or marble kits that you get and use for 3 months, where you learn all about something and have these kind of hands-on demonstrations students do for themselves, following a procedure or a picture diagram and create something. That's just, going through the motions of carrying out a task to gather some specific data. It's not engaging students in a particular problem or question, which then the students have to really, in almost a free-form sense, using logic, that structure of science and engineering, apply their science and engineering practices to analyze a scenario authentically in a way they haven't seen the answer to this before, and gather the necessary data, really analyze it, and evaluate the scenario to form an evidence-based conclusion. That's what mastery is all about. Performance readiness is like, we learn all about rocks and minerals, and then we're going to, because we've learned that rocks and minerals all have different hardnesses based on, or properties based on which rock or mineral, we're going to go through and, we're going to learn how to do a scratch test. So we're going to scratch all the different minerals, and then we're going to, do a streak test and streak them all. That's how we can figure out which is which. Mastery readiness is more like this having to deal with a scenario of a general contractor making a plan to or an architect designing a commercial kitchen that a general contractor is going to have to install, and needing to decide, based on the fact this is a commercial kitchen, which countertops to use because durability is so important, and having a table of data based on different types of countertop materials, and coming to maybe there's 3 different opinions about which countertop material to use. Can your student, the real student, look at the scenario, analyze, evaluate that data, the scenario, the needs and constraints, and form a conclusion of their own, having analyzed the evidence and put evidence forward to support the claim, and then reason it? Okay, that's what we're talking about. And we've done this for, like I said, over 10 years at this point. And the reason that we're next generation aligned at this point is because as the releases and recommendations and reports have been coming out since 2006, 2007, we've been developing all of those components into our curriculum just because it's just good teaching and learning. It's quality instruction, and as a result of that, what you see is, as in the case of art, you see connection between all the disciplines, these higher order thinking skills creating value. But what you see beyond that is even under the assessments like NECAP, which are not aligned yet to NGSS, major data gains in performance above state averages. And this is an example I like to use from Massachusetts, where the state average for advanced and proficient, so students who are exemplary, proficient, that average is only 50%. And here's an example where the district goes from average to well above average. And you can see those immediate gains and how they're sustained over time. Now this district is only 20% high needs and 7% low income. If we look at an urban district where 35% of the children don't speak English as their first language, where 72% are low income, 65% are free lunch, 75% are high needs, you see those students going from below average, remember average being 50%, to above average and really well above average, adding 51 points to the level of advanced and proficient students in that school. Now you see a decline here, these shocks, and the reason you see those shocks is because there are changes in teachers in that school and administrators in the district and such, that it has an effect. However, what I want to point out is that they're not only still above average, but when they have had a shock, they don't fall all the way back to where they were. The fact that students have been nurtured intentionally this way and that they are developing skills, they're able to take what they have learned in the past, because again, we are intentionally developing, building on what students know. They're taking what they know and they're still making progress, and that's why you see a positive trend here against the requirements of the testing. So still well above the state average. And I'll pull up a really low level middle school just to point out the gains that are made there, because middle school always is a spot where data dips. Now when you look at the 26 highest states in the 26 largest cities in Massachusetts, the average level of proficiency is like 26%. Okay, over the course of 2 years, this school goes from 4% proficient, 0 exemplary, to 28%. So adding 24% of their student body into those upper tiers, where they're actually more than treading water now. The lowest levels, the basic, below basic, warning, failing levels, the students drop, the percentage of the student body that was there before they used this was 54%, and it dropped, basically cut in half to 27%. So that's why you see these major shifts. So we're this is the most recent data, so we're hoping for a positive trend to continue. But this is a very difficult, it's a challenging environment to get these kinds of gains. So to see the gains and to see really the impact of kind of student thinking being on the forefront, the way that we're talking about transitioning to a next generation inquiry model, you see 64% of the students in the school, their first language is in English. 15% are still learning English. They're English language learners, ELLs. 95% are low income, 87% are free lunch, and 97% are high needs. So really difficult, and you can see that drop-off is really huge. When we look at NECAP states like Vermont, you can see here in New Hampshire, our children are in purple and in yellow, and you can see those subgroups, right? Physical, earth, life, inquiry. Look at how our students are outperforming the state average, and this is, this is in 08 and 09 and so on. State compared to us, or it's really not us. It's teachers and students who are engaged in KnowAtom. You can see outperforming 20, almost 30% in some cases. And look at the inquiry portion, so on. It's those thinking skills is where the difference gets made. And New Hampshire being very similar to Vermont in the sense of proficient, or when we were talking about proficient and advanced, that's proficient and proficient with distinction versus partially proficient or substantially below, which would be the kind of developing or warning and needs improvement categories. So very, very similar, and it's kind of interesting to see the drop-off again that 32% is the state average in Vermont for proficiency. Grade 11, 30%, grade 4, 47%. So, you know, these students are performing significantly better. Nonetheless, I will leave it there. If you have any questions, feel free to reach out. If you have any questions about our material or examples I've used, or you'd like to reach out to me, feel free to do so through Mary Ellen DeLacy. She's a curriculum specialist here at KnowAtom. Her email is mdelacy@knowatom.com, and her telephone number is 617-475-3475, extension 2006. There's another webinar I'd recommend in the series, which you can get free and on demand. It's strategically implementing those next generation science standards in your classroom. So you can get to that by knowatom.com/strategically. And there's a bunch of other resources you can engage as well that are free and on the website. I mentioned the curriculum and readers, which you can get at knowatom.com/curriculum. Again, it's only a month that you have the free access to the first month of the year. All the others are available, but again, for purchase. You can check out case studies to see more up close about schools that use the program and what that all looks like. Staying connected, you are welcome to subscribe for free to our blog. Follow us on KnowAtom, Facebook/KnowAtom, Facebook.com/KnowAtom. That's a great way to stay connected with resources. Follow us on Twitter @KnowAtom's our handle. When you go to KnowAtom.com, at the top of the screen you'll see resources. That's where you can get those additional free and live and on-demand resources, ebooks, all kinds of stuff. You'll see STEM curriculum. You scroll down, that's where you can get the curriculum too. And you'll see blog, that's where you can subscribe. Thanks a lot. I appreciate your time. And if you do have questions, feel free to reach out to Mary Ellen. My name's Francis. She'll get that to me if you just mention my name, and I will respond to you personally. Thanks a lot. I hope you enjoy your day and really wish you the best of luck as you master the next generation science standards